Every single year, factories across the planet churn out more than 430 million metric tons of plastic. Picture that number as a chain of freight trains long enough to circle the Earth 7 times over, and you start to grasp the scale of it. Now, here's a fact that catches most people off guard. Less than 10% of all the plastic humanity has ever produced has actually been recycled. The other 90% is still out there somewhere, sitting in landfills, drifting through oceans, or breaking down into fragments so small that scientists have started finding them inside human blood, lungs, and even arteries. A substance that didn't exist in everyday life a century ago has now worked its way into our bodies, and nobody signed up for that. Then, in October of 2025, something happened that made engineers around the world stop scrolling and start paying attention. A small research group based at a forestry university in northeast China published a paper claiming they had built an entirely new type of plastic out of bamboo. Not a bamboo and oil blend, not a partial substitute padded out with plastic fillers. A material that is 100% bamboo, stronger than the plastic sitting in your kitchen drawer right now, compatible with the injection molding machines already running in factories worldwide, and capable of fully vanishing into ordinary soil within 50 days. If stories about discoveries that flip an entire industry on its head are the kind of thing you enjoy watching, tapping the like button genuinely helps this channel keep making them, and subscribing means you won't miss the next one. To understand why this claim is such a big deal, you have to back up and look at the bigger picture first. You need to see how plastic quietly took over every corner of modern life, why decades of attempts to replace it have all crashed into the same obstacle, and what exactly separates this bamboo breakthrough from everything that came before it. Only then does the scale of what happened in that lab in Harbin really sink in. Start by looking around you. The phone in your hand, the container your leftovers are sitting in, the shell around your laptop, the dashboard of your car, all of it traces back to the same source. Plastic is everywhere, and that didn't happen by chance. It spread because it does things that no other material can match. You can melt it down and pour it into virtually any shape imaginable, whether that's a bottle, a mechanical gear, a car bumper, or a microscopic clip buried inside a piece of medical equipment. It's astonishingly cheap to produce. Unlike metal, it doesn't corrode. Unlike wood, it doesn't decay. Unlike glass, it doesn't shatter the moment you drop it. It seals out water, insulates electrical wiring, and holds up whether it's baking in the sun, sitting in a freezer, or getting soaked in the rain. Healthcare depends on this material in ways that rarely cross people's minds. Every syringe, every IV bag, every sterile wrapper protecting a surgical tool from contamination. Plastic makes it possible. Strip that material out of a hospital and modern medicine would struggle to keep functioning the way it does. Food supply chains lean on it just as heavily. A layer of plastic film can keep a loaf of bread edible for weeks instead of days. It lets produce travel across continents without spoiling along the way. It keeps beverages sealed and medication uncontaminated. So when someone suggests we simply stop using plastic altogether, the honest response is to ask what else could realistically do all of that while still costing almost nothing to manufacture. So far, nothing has come close to answering that question. That's precisely why replacing plastic is such a monumental challenge. You're not swapping one ingredient for another, you're trying to replace the connective tissue holding together nearly every system in the modern world. Imagine trying to pull every nail out of every building in an entire city. For a while, nothing looks different. Then, everything starts to collapse at once. But there's a catch buried inside all of this convenience, and it's a serious one. The very quality that makes plastic so valuable, its refusal to break down, is also what makes it dangerous. A bottle you throw in the trash today will still be sitting in a landfill hundreds of years from now, long after you, your children, and their children are gone. It doesn't vanish. It just keeps splitting into smaller and smaller fragments, eventually shrinking down to pieces too tiny to see with the naked eye, but more than small enough to slip into rivers, soil, and living tissue. Fish swallow these fragments. Birds ingest them. Humans breathe them in or absorb them through food and water without ever noticing. The exact material that built the modern world is now quietly accumulating inside the creatures living in it, and researchers still don't fully understand what that means for long-term health, so the world finds itself boxed in. Nearly everything we've built depends on a material that never truly disappears, and every year we manufacture even more of it. Finding a genuine substitute isn't a matter of environmental politeness anymore. It's a response to the fact that plastic particles are now showing up inside our own bloodstreams, and that isn't a problem that resolves itself with time. Solving it, though, has proven far tougher than anyone expected. Every previous attempt at a replacement has slammed into the same wall, and understanding exactly what that wall is made of is where this story turns next. The bioplastics industry has spent decades throwing solutions at this problem, and almost every one of them has failed in an identical pattern. Researchers keep landing on materials that are either strong but refuse to break down, or ones that break down easily but are too fragile to actually use, or ones that manage both but cost so much to produce that nobody can afford to buy them at scale. Untangling why each of these attempts stumbled reveals just how narrow a target the Harbin team actually hit. Take PLA, short for polylactic acid, probably the most well-known bioplastic on the market. It's derived from fermented cornstarch, and yes, it can decompose, but only under very specific conditions, inside an industrial facility that holds the temperature above 58 degrees Celsius for weeks at a stretch. Toss a PLA cup into your backyard compost, or an ordinary landfill, and it will sit there essentially unchanged for years, behaving exactly like conventional plastic, despite its green marketing. PLA carries other baggage too. It's brittle, snapping easily if dropped. It can't tolerate much heat before warping. And because it's derived from corn, producing it in large quantities means dedicating farmland to growing plastic instead of food, which is a difficult trade-off to justify while food insecurity remains a global issue. Then there's PHA, or polyhydroxyalkanoate, which solves the biodegradability problem more convincingly than PLA does. The catch is cost. Producing PHA requires cultivating bacteria through a complex biological process, which drives the price up to several times that of ordinary plastic. When a material costs 5 times more than the thing it's supposed to replace, manufacturers simply won't adopt it at any meaningful scale, and PHA has spent years stuck making small batches for niche applications as a result. Starch-based plastics run into a different wall entirely. They dissolve or fall apart when exposed to water, which rules them out for anything that might get wet. Picture how useless a water bottle would be if rainfall could melt it. Cellulose acetate, meanwhile, is genuinely strong, but manufacturing it requires harsh chemical treatments, which undercuts the whole point of building something environmentally friendly in the first place. Look closely, and you'll notice every single approach keeps hitting the same three-way trade-off. You can engineer something strong. You can engineer something biodegradable. You can engineer something cheap. Nobody had figured out how to combine all three simultaneously. The obstacle here wasn't a shortage of creative ideas. It was chemistry itself at its most fundamental level. Nobody had cracked the code for taking raw plant material and restructuring its molecular building blocks into something that behaves like plastic without dumping in extra chemicals that would erase the entire environmental benefit in the process. Think of it like staring at a pile of raw lumber and being told to turn it into a steel beam. The wood is right there in front of you. Steel is a real, achievable thing. But you can't just bend or reshape the wood and call it steel. You'd need to fundamentally alter what that wood is made of at the molecular level, breaking it down and reassembling it into something structurally different. That's essentially the challenge nobody had solved for plant fiber and plastic, and it's precisely the wall that a team of researchers in Harbin, China finally broke through. The method they used to pull it off is what made engineers across the world stop mid-scroll and pay very close attention. The breakthrough didn't come from where anyone expected it to. It wasn't born inside a massive oil corporation's research division. It wasn't cooked up in a Silicon Valley startup. It didn't emerge from a classified government facility either. It came out of Northeast Forestry University in Harbin, an institution primarily known for studying trees and forest ecosystems, not cutting-edge materials science. The two researchers leading the project, Haiying Wu and Da Zhou, teamed up with colleagues at Shenyang University of Chemical Technology to attempt something with bamboo that most materials scientists had quietly given up on years earlier. To understand why bamboo had been written off, you need to understand what makes it so structurally stubborn. The core building block inside bamboo is a substance called cellulose, the same material that gives structure and rigidity to trees, leaves, and blades of grass everywhere. Inside bamboo specifically, those cellulose molecules are locked together by an extremely tight network of hydrogen bonds. Those bonds are the reason a bamboo stalk can stand upright and hold weight, even when strong winds are pushing against. But that same molecular rigidity is exactly what makes bamboo so resistant to reshaping. The cellulose is essentially frozen in place. You can't melt it down and pour it into a mold the way you would with conventional plastic. Force bamboo into a new shape and it snaps rather than bending, which is why every earlier attempt at bamboo plastic took a shortcut instead of solving the actual problem. That shortcut usually involved grinding bamboo into fibers and mixing them into standard plastic resin. The bamboo added some structural reinforcement, sure, but the petroleum-based resin was still doing the real work of holding everything together. The end result was half bamboo, half oil, a blend, not a genuine replacement. And because it still contained conventional plastic, it never actually decomposed in nature the way true bamboo would. This is exactly where Wu and Zhou's approach diverges from everything that came before, and that divergence is where the real story begins. Rather than blending bamboo with plastic, the Harbin team found a way to convert bamboo directly into plastic using a two-step process that turns out to be almost deceptively simple once you understand the logic behind it. The first step involved soaking bamboo cellulose in a specially formulated liquid made from zinc, chloride, and formic acid. What this liquid does is remarkable. It dissolves the hydrogen bonds, locking the cellulose molecules into their rigid structure, but it leaves the molecules themselves completely intact. Picture it like carefully loosening a tangle of knots in a fishing net without cutting a single strand. The net is still whole. The string is just as strong as before. It simply isn't locked into that stiff original shape anymore. The second step introduces ethanol into the mixture, and this is where the real transformation happens. The ethanol acts almost like a matchmaker, guiding the now loosened cellulose molecules toward each other so they can reconnect in an entirely new configuration. As they link back up, the bonds that form are actually tighter and stronger than the ones present in the bamboo's original structure. In effect, the molecules rebuild themselves into something better than what they started as. What comes out the other end looks, feels, and performs like conventional plastic, yet every bit of it originated from molecules that were already present inside the bamboo to begin with. No synthetic adhesives were introduced. No petroleum-derived chemicals were blended in. No toxic byproducts were left behind in the process. The researchers named their creation BM plastic, short for bamboo molecular plastic, a label that captures both its origin and the method used to produce it. Of course, a clever process and a compelling backstory only go so far without hard evidence to support them, and it's the numbers coming out of this research that truly rattled the engineering world. Laboratory materials often look impressive on paper, and then fall apart the moment someone tries to apply them outside a controlled setting. BM plastic didn't follow that pattern. Its performance data was strong enough that engineers who had spent entire careers working with petroleum-based plastic had no choice but to take it seriously. A material developed at a forestry school outperforming conventional plastic in strength testing isn't something anyone in the field was prepared for. The tensile strength numbers alone are difficult to dismiss. BM plastic can withstand a pulling force of 110 megapascals, roughly double what PLA, the corn-based bioplastic, can handle. It also surpasses high-impact polystyrene, a plastic used constantly in everyday consumer products. For context, a strength rating of 110 megapascals starts approaching figures associated with certain grades of steel and aluminum used in vehicles and aircraft. This isn't a delicate, easily cracked plant-based novelty. It's a legitimate structural material capable of bearing real load. Resistance to bending held up just as well under testing, with BM plastic scoring 6.41 gigapascals, meaning it doesn't warp or sag under applied pressure. It actually outperformed ABS in this category, the tough plastic used in car dashboards and in the Lego bricks people dread stepping on barefoot. If you've ever felt how much force one of those bricks can withstand underfoot, you have a rough sense of how sturdy ABS really is, and BM plastic holds its shape even more effectively under stress. Heat resistance turned out to be another strong point. BM plastic maintains its structural integrity at temperatures exceeding 180 degrees Celsius. Researchers left test samples exposed to 100-degree heat continuously for 7 full days, and not a single crack appeared. They also submerged samples in a strong acid solution, and the surface came away completely undamaged. Try that same test with a PLA cup, and it would warp, crack, and disintegrate within days. BM plastic simply sat there, unaffected. The material also showed a strong capacity to absorb energy before breaking, a property scientists refer to as work of fracture. BM plastic scored 80 kilojoules per cubic meter on this measure, outperforming both conventional plastic and most bioplastics currently on the market. In practical terms, that means the material can take a real impact without shattering, which matters enormously for products like car components, phone cases, tool handles, or anything else likely to get dropped or knocked around during daily use. Then comes the statistic that grabbed the most attention from people focused on environmental impact. BM plastic broke down completely in ordinary soil in roughly 50 days. No industrial composting facility required, no special processing plant. Just plain dirt, the same way a fallen leaf gradually returns to the earth. Within about 50 days, the material was essentially gone. And there's an even more surprising twist buried in the data. When researchers recycled the material using the same chemical process used to create it, the recycled version retained about 90% of its original strength. Standard plastic loses strength every single time it gets recycled, which is exactly why recycled plastic so often ends up in low-value applications like park benches rather than higher performance products. BM plastic doesn't suffer that same degradation. You can put it through the recycling loop repeatedly, and it stays nearly as strong as it was the very first time it was produced. The research team published every one of these results openly in Nature Communications, laying out each test, each measurement, and each step of their process for anyone in the world to scrutinize and verify independently. They weren't asking anyone to simply take their word for it. Impressive lab results mean very little, though, if the raw material behind them can't support manufacturing at a massive scale. And this is exactly where bamboo pulls ahead of nearly every other plant on Earth. The choice of bamboo for this project wasn't arbitrary or convenient. You couldn't simply substitute a different plant species and expect the same outcome, because bamboo possesses a rare combination of physical properties suited to this exact chemical process, paired with a supply chain that's already fully operational and ready to scale immediately. Bamboo grows faster than any other plant known to science. Certain species can shoot up more than 1 meter in a single day. That isn't an exaggeration or a typo. It's genuinely visible if you sit and watch closely enough. Once harvested, it regrows directly from its existing root system, meaning there's no need to replant seeds, clear fresh land, or install new irrigation infrastructure. A bamboo forest fully regenerates within 3 to 5 years after being cut down. Compare that to a pine forest, which needs 25 to 30 years to reach a harvestable size, or a corn crop, which has to be planted completely from scratch every single growing season. Bamboo simply keeps regenerating on its own, cycle after cycle, without that repeated investment. Bamboo also produces roughly 5 times more biomass per hectare than a standard timber forest, and it pulls carbon out of the atmosphere at a rate matching or exceeding many species of trees. It thrives on land unsuitable for conventional agriculture, meaning it doesn't compete with food crops for space. A significant advantage considering how often corn-based bioplastics like PLA get criticized for consuming farmland that could otherwise be growing food. China happens to hold the largest bamboo resources anywhere on the planet, with more than 7.5 million hectares of bamboo forest spread across roughly 20 provinces and over 500 distinct species under cultivation. The country's existing bamboo industry already generates close to 320 billion yuan annually and supports the livelihoods of more than 7.5 million farmers. In other words, the entire infrastructure for growing, harvesting, transporting, and processing bamboo already exists at enormous scale. Nobody needs to build that system from the ground up. This point matters more than it might initially seem. Plenty of promising new materials fail, not because the underlying science doesn't work, but because there's no realistic way to produce enough of the raw ingredient affordably. A brilliant new material that depends on some rare plant growing in one isolated corner of the world will never scale up enough to displace hundreds of millions of tons of petroleum plastic. Bamboo doesn't have that limitation. It grows across huge stretches of Asia, Africa, and South America, with roughly 22 million hectares of bamboo forest existing worldwide across dozens of countries. It's already being harvested at massive scale for building materials, furniture, flooring, paper products, and textiles, meaning the logistics of growing, cutting, transporting, and processing it are already functioning smoothly in many regions. Companies looking to adopt bamboo plastic wouldn't need to construct an entirely new supply chain from nothing. They could plug into infrastructure that's already running. So bamboo occupies a genuinely rare position. It's simultaneously suited to producing strong plastic and available in overwhelming abundance right now, combining performance, supply, and an established agricultural system into one package. But having the right raw material and the right chemistry solved still leaves one crucial question unanswered. Can this material actually be manufactured inside ordinary factories using equipment that already exists on production floors around the world? Achieving strong results in a laboratory setting is one accomplishment. Manufacturing that same material reliably inside a real factory using real production equipment is an entirely separate challenge, and it's exactly where most bioplastics have historically failed. Many require specialized machinery that standard plastic factories simply don't have on hand. BM plastic doesn't run into that obstacle. It can be processed through injection molding machines, the same equipment responsible for producing the vast majority of plastic products manufactured today. It can be cut, drilled, and shaped using conventional tools, and it can be pressed into flat sheets or molded into complex three-dimensional forms. To prove this wasn't theoretical, the research team manufactured lampshades, mechanical gears, packaging containers, and decorative items using entirely unmodified, off-the-shelf machinery. That detail carries enormous weight. Most bioplastics require entirely new production lines, custom molds, or specific operating conditions that conventional plastic factories simply can't accommodate, forcing companies to sink millions of dollars into new equipment before manufacturing a single finished product. BM plastic sidesteps that expense entirely. If a facility already owns an injection molding machine, it can theoretically begin producing bamboo plastic products almost immediately without waiting on new infrastructure. The process also runs at room temperature, which might sound like a minor technical detail, but actually carries significant economic weight. Heating raw plastic is one of the largest cost drivers in conventional manufacturing, with factories relying on massive ovens and industrial-scale heaters to melt their material before shaping it. BM plastic requires none of that. There are no superheated kilns, no pressurized tanks, no giant heating systems involved anywhere in the process, which translates directly into substantial energy savings. The chemicals driving the transformation, zinc chloride and formic acid, are widely available and inexpensive, and the ethanol used in the second step can be captured and reused rather than discarded. Nothing in the entire process depends on rare or costly materials. Researchers estimated that producing BM plastic currently costs around $2,300 per ton, compared to roughly $1,200 per ton for conventional plastic. Almost double the price sounds like a serious barrier at first glance, but two factors narrow that gap considerably. First, production costs tend to fall sharply as manufacturing scales up and becomes more efficient, a pattern that plays out with nearly every new material or technology entering the market. Second, that $1,200 figure for standard plastic doesn't account for its hidden costs. Factor in the expense of cleaning up pollution, addressing health complications linked to microplastic exposure, and complying with tightening government regulations, and one study projects the true cost of conventional plastic could climb to roughly $2,400 per ton by 2040. Viewed that way, the gap between the two materials starts to look far less intimidating and possibly reversible within just a few years. China's response to this discovery has moved remarkably fast, largely because the groundwork was already being laid years in advance. Back in 2022, the government introduced an initiative aimed at replacing conventional plastic with bamboo-based alternatives, followed in 2023 by a formal 3-year action plan. Tangible products are already reaching the market as a result. Exports of bamboo fiber tableware climbed 35% in 2025 alone. Cities have begun installing bamboo piping as a substitute for steel and concrete in certain applications. Engineers even flew a functioning drone with bamboo, making up 25% of its body structure, and the resulting aircraft weighed 20% less than an equivalent carbon fiber model while costing roughly a quarter as much to produce. Meanwhile, international negotiations toward a global plastics treaty collapsed in 2024, with participating countries unable to agree on binding limits for plastic production. The takeaway from that failure is fairly blunt. Waiting around for international regulation to fix this problem isn't a realistic strategy. Whichever countries and companies manage to build a viable replacement first stand to control the market that follows, and China appears determined not to be left behind in that race. That said, real obstacles still remain ahead. BM plastic, in its current form, is rigid, a great fit for solid structural components, but not yet suitable for flexible applications like plastic wrap or thin, pliable bags. Researchers also still need to fine-tune how long the material lasts during active use before it starts breaking down after disposal, since a product that decomposes too early during its functional lifespan would obviously defeat its purpose. And scaling a laboratory process up to industrial output measured in millions of tons is an enormous undertaking that will require years of engineering refinement and substantial financial investment. None of these challenges are minor, and none of them should be glossed over. Even so, no bioplastic developed up to this point has managed to combine this particular mix of qualities. This level of mechanical strength, this rate of natural decomposition, this degree of recyclability without losing performance, this level of compatibility with existing factory equipment, and this scale of raw material supply, all bundled into a single material. Other alternatives have typically delivered one or two of these traits at the expense of the rest. BM plastic appears to be the first candidate that doesn't force that trade-off, at least based on the data published so far. It took roughly a century for the world to build its entire infrastructure around plastic, and that dependence isn't going to disappear overnight, regardless of how promising this new material looks. But for what may be the first time, there's a genuine option on the table that delivers stronger performance and better environmental outcomes within the same package, rather than forcing a choice between the two. It doesn't ask manufacturers, consumers, or entire industries to sacrifice something they already rely on. It offers a straightforward upgrade instead, comparable or superior functionality without the centuries-long environmental cost attached to it. And that, more than any marketing claim or headline, is what meaningful change in materials science actually looks like when it finally arrives. Step back and consider the full arc of this story. Plastic conquered the modern world because nothing else could match its combination of low cost, durability, and versatility, and that same durability turned into an accumulating liability the moment scientists started finding fragments of it inside human blood and tissue. Every serious attempt at a replacement over the past several decades ran into the identical trade-off: strength without biodegradability, biodegradability without strength, or both traits present but priced out of practical use. What changed in Harbin wasn't a lucky discovery, so much as a genuinely new chemical process, one that dissolves and rebuilds the molecular bonds inside bamboo cellulose, rather than simply blending bamboo fiber into existing plastic resin. That distinction, transformation instead of imitation, is the reason BM plastic manages to outperform steel-adjacent strength benchmarks, resist heat and acid, absorb impact without shattering, decompose fully in ordinary soil within about 50 days, and retain nearly all of its strength through repeated recycling. None of that would matter on a global scale without bamboo's practical advantages layered underneath the chemistry. A plant that regenerates from its own root system in 3 to 5 years, grows on land unsuited to food crops, produces roughly 5 times the biomass of a standard timber forest per hectare, and already supports a massive, functioning agricultural and industrial supply chain across China, and dozens of other countries, removes the single biggest obstacle that has doomed nearly every previous bioplastic attempt: the inability to produce enough raw material, affordably, at the scale required to actually replace petroleum-based plastic. And because the resulting material runs through standard injection molding machines at room temperature, factories don't need to overhaul their equipment or absorb massive upfront costs just to start producing it. Real challenges remain before this becomes a true global replacement rather than a promising early-stage material. Its current rigidity limits it to structural applications rather than flexible packaging or thin films. Its in-use lifespan still needs further engineering before widespread commercial deployment. And scaling any laboratory process up to the level of millions of tons annually is a slow, capital-intensive undertaking that will take years to fully mature, regardless of how strong the underlying science looks today. Those limitations are worth stating plainly, because overselling a breakthrough before it's actually proven at scale tends to backfire once reality catches up with the hype. Still, taken together, what the Harbin research team demonstrated is something no earlier bioplastic has managed to pull off: a material that combines genuine structural strength, complete natural biodegradability, durable recyclability, compatibility with equipment already sitting on factory floors, and access to a raw material supply chain that spans continents and already operates at industrial scale. Individually, other bioplastics offered pieces of that equation. None of them, until now, have offered all of it at once. Whether BM plastic eventually scales into a genuine global replacement for petroleum-based plastic, or ends up as one important step among several toward that eventual goal, the significance of this research goes beyond bamboo itself. It's a reminder that the raw materials for solving some of the most stubborn problems facing modern industry may already be sitting in plain sight, waiting for someone to ask the right chemical question. A grass capable of growing a meter in a single day sat overlooked for decades while the world searched for exotic, complicated solutions to the plastic problem. That alone is worth sitting with for a moment. If this video shifted how you think about something you touch dozens of times every single day without ever considering where it actually came from, tapping the like button and subscribing genuinely helps this channel keep producing content like this, and turning on notifications means you won't miss whatever comes next. There are related videos on screen right now if you want to keep exploring this topic. And here's a question worth sitting with. If a fast-growing grass was the answer to the plastic crisis the entire time, quietly available and largely ignored, what other solutions might already be hiding in nature, waiting for someone to ask it the right question? Leave your thoughts in the comments below.